Hey guys, let's start for this example here. What you asking to identify the net magnetic force directions based in the loop located in the magnetic field that point to the page. And what we're gonna do, we have the current clockwise. So the first part here is our current. That's the current goes from my loop. And I will use the my loop part by part. So let's start from the first part here. When I have this branch of this side of my loop, the directions, we're going to use the right hand rules. The velocity is the same direction of the current. Magnetic field point down, so I will use the right hand rules. I will find the force will be point in this directions. Similarly, I will use the same concept for this part. I will find the force will be point in this directions. And now the left side of my loop located out of the magnetic field, so there is no magnetic force will be exist in this part. So the only two components here, two components. So y component will be cancel each other. So the only component we have it's the component in the right. So here is the F and to the right. So let's now play our topic here for the magnetic force when you have moving a charge with the same concept that we covered before. And here just we have the conductors and we have second conductors as the rod here, as the part located in the top of my conductors as the U shape. And in both of the conductors, they are located in magnetic field point out of the page. And we move in the rod here by certain velocities point down. I will use right hand to identify based in that, for example, here's a positive charge. And I would identify the force of the positive charge in that case. So what the direction for the force? Right hand. So I use the right hand, I will find the force located in this direction. So basically what that means, that my positive charge will be in this side. And similarly, negative charge, right hand rules will be point in the other side. So from that case, since they are located in the conductors, we assume it's the zero resistance. So we create a path to my current or my charge move in this path. So what that basically means, we create an electric circuit. So we have the current, we generated a current that has this direction based in the moving conductors inside the magnetic field. So let's see other example beside the previous one. So here is the first or the A we already covered in the previous slide. So now let's move for the P, and we apply the same concept here. So we have the positive, we have the right hand rules, magnetic field point toward the page, and here we have the positive charge. Apply the right rules, so we're gonna find the positive charge will be this way. Similarly, for the negative charge will be in the top one. And we're gonna use the same right rule or right hand rules for this part here. We'll find the positive charge will be point up, negative charge will be in the lower part. So what does that mean here? We create a path, and when you come here, it's gonna have the same path. And here is the same path. So basically we create induced current using the move in the conductor inside the magnetic field. We create a current, what we call induced current inside that conductors. Let's move for the C. So for the C here, so we have the formula for sine alpha. Here is the alpha, the same angle. So I have 0, 0 angle. So from here, the magnetic force will be 0. So as a result, there is no induced current. Induced current. Let's move for the complicated one here. Is when I have 3 rods located in the magnetic field, and every rod has his own velocity. So we're gonna use the same concept, positive charge in each part, and just to identify the direction of the positive and negative charge. So from the first part here, right hand rules, will identify the negative charges here and a positive charge here. And the second part, negative right-hand rules, it has these directions here. And the last one will be right-hand rules. Double check with that it's right. So now my current here is gonna be going this path, and will be continuous moving from this path and this. So the induced current, we generate induced current with that circuit as well. So let's move for the second example here, or the D example here. Right-hand rules, here positive charge, and here is a positive charge. Right-hand rules, my magnetic field point to the page, my velocity, my time point down. I will find my force, or the magnetic force, pointed in the right side. So here is me in the positive, and here is the negative. Similar for this one, it has the same direction. Magnetic force will be to the right. That means positive charge here and negative charge here. So here I have negative charge in the same direction, positive charge in the same direction. So there is no current as well, no induced current here as well. Let's move for the last part here for the E. And just make sure, guys, all the situations what we covered before, the conductor is located in magnetic field. And here's my conductors, part of it located magnetic field. By my part that I moved in the top of my conductors, it is not located in the magnetic field. So here is there is no current as well. No induced current as well. So basically what we have here, now we identified the directions. Now we need to calculate it, or write it down, a formula to find the magnitude of the EMF, or the motional EMF. Last time we talking about this one, where the direction for the positive and negative charge, we create a batteries based on the positive and negative charge inside the conductors as the chemicals. Now, depending about some parameters, that's the formula that you need to identify or to calculate. We call it the motional EMF, or sometimes we call it delta V motional, or the EMF. It's dependent about the velocity of moving the conductors, dependent about the length of the conductors, and dependent the magnetic field of the conductors that located in the conductors. So those three parameters with that. So let's apply a numerical example for that case. So here is what we have. We have the conductors connected with the resistors, 2 amps, located in the magnetic field point out of the page. And we have a rod. We pushed that rod with the certain velocity, 0.5 meter per second, and magnetic field, 0.5 Tesla. And we need to find the induced current. I don't have the formula for the induced current. For this case here, I can just use my right hand, as the previous example that we did, to identify what the direction of the induced current. So from here, we will find the positive charge will be force will be point down. So that means positive charge here, negative charge here. That means my induced current will have these directions. You're gonna move in that directions. That's my induced current. How we find it? So the first one, we find the EMF, or the delta V or motionals. It has a dependent about the velocity, velocity times the length of the conductor times the magnetic field. I have the velocity 0.5 times the L, it's 10 centimeters, and times the magnetic field will be 0.5 Tesla. If you multiply those three numbers together, you will end up with the 0.25 volt. And if you see this value, it is very small, even less than the small battery. So in that EMF, or the potential with the source of the energy, 0.5, it's very small. Now I can create my circuit based on that. So I have my circuit right now, negative. I will use the same directions that I created here, negative and positive. and it's connected to my 2 amps resistors. Here is a 2 amp. Now my EMF right now, it's 0.025 volt. My induced current, it has this directions. Here is the I. I can find I using the Kirchhoff law in this loop, or use the one single resistor, one single volt. I can find the current. So either way. So here is the current, will be the EMF divided by R. So I have here is the 0.025 volt divided by 2 amps. We end up with the 125 milliamps. The current is very small. So similarly, if you want to increase my current, I have to increase my EMF, increase my EMF. So even I increase my magnetic field, or I increase the speed of moving the conductors. That's the way how we generate the more EMF, or the motional EMF. I'm done for this lecture, guys. Thank you, and see you next video.